So this is differential equations in physics course. So we are together in this course. I am the instructor. My name is Hikmet Yükselici. I am the instructor for this course for this semester. Okay, so let me give you first the textbook we are going to study. Okay, so the textbook is this one here. Let me. It's here. So this is the textbook. The title of the textbook: Differential Equations by Ross, 3rd edition, published in 1984. Okay. So there are many chapters in this textbook, 14 chapters. Okay. So we are not going to cover all, but let me give you a list of chapters we are going to cover. Okay. So this is syllabus for this course, right? Okay. So first week we start with fundamental methods and applications, differential equations and their solutions, classification of differential equations, their origin and application, solutions, initial value problems, boundary value problems, and existence of solutions. So this is the chapter 1 of this textbook. Okay, so this is introduction chapters. Okay, in the second week we study with the second chapter. Okay, first order equations for which exact solutions are obtainable, exact differential equations and integrating factors. So this is second chapter in the textbook, second week. Okay. Third week, we are going to continue studying chapter 2. So this chapter 2 is a long chapter. So we are going to study on this chapter. We stay on this chapter for 3 weeks, yes. Second, third, and fourth weeks. So we study second, third, and fourth weeks. We study this chapter 2. Chapter 2 is quite involved chapter. Okay, so in chapter 2 we study second week. We study first order equations, right? And in the third week, linear equations, separable equations, and equations reducible to this one. So again, these are on chapter 2. On fourth week, Bernoulli equations, special integrating factors and transformations. This is again chapter 2. And we are done. After fourth week, we are done with chapter 2 and continue with chapter 3 in the same textbook. Applications of first order equations, orthogonal and oblique trajectories, problems in mechanics, rate problems. These are all in chapter 3. And chapter 6, week 6, right? So explicit methods of solving higher order linear differential equations. Basic theory of linear differential equations. So this is chapter 4 in this textbook. And we continue studying chapter 4 next week. After next week, 7th week. Homogeneous linear equation with constant coefficients. Again, this is week 7, chapter 4. So after that, we are going to have a midterm exam, okay? Midterm exam. This is 8th week. And we continue studying after the midterm exam. We continue studying chapter 4 again. The method of undetermined coefficients, variations of parameters, the Cauchy-Euler equation textbook, chapter 4. So week 10. Physical applications of second order linear equations with constant coefficients, the differential equation of the vibrations of a mass on a spring, free undamped motion, forced motion, resonance, phenomena, electric circuit problems. These are all in chapter 5. So 11th week, we study series solution of linear differential equations. This is chapter 6 of the textbook. And 12th week we continue with studying chapter 6, Power series solutions about an ordinary point, textbook 6. So, and chapter 13, week 13, we conclude chapter 6. 13 and 14 week. We again study chapter 6, series solution of linear differential equations, power series solution about an ordinary point, solutions about singular points, the method of Frobenius. And in the 14th week, we continue the method of Frobenius. And then after that, we are going to have a final exam. Okay, this is the syllabus. Okay. But what I think, possibly we will have 2 midterm exams, okay? 2 midterm exams and 1 final. And I am not sure about that. I'm going to ask to the department. So if we can do, we can hold a second midterm exam. Okay, we are going to think about that. I'm not sure about that. I'm going to think. Okay. So any question about the content? Also, I'm going to assign homework sets. Okay. And there are also many examples, problems in this textbook. Okay. I'm going to assign the homework problems from this textbook. Okay. So you can get a copy of this textbook, legal copy, on the internet. Okay. Okay. Any question? Okay. Now let's conclude this section and continue with chapter 1. So we start studying differential equations with chapter 1. So in chapter 1, differential equations and their solutions. Okay. So what we do in this chapter, the purpose of this chapter is to introduce the student the basic aspects of subject, theory, method, and application. Okay. So we are going to classify differential equations and see their origin and application. Okay. So first of all, let me give you definition of a differential equation. Right. An equation involving derivatives of one or more dependent variables with respect to one or more independent variables is called a differential equation. Okay. So let me give you examples of differential equation. Example. This is the first example from the textbook, right? Okay. So this is a differential equation. D square y, second derivative of y with respect to x, plus x times y dy over dx squared. We set this equal to 0. So this is the differential equation. Okay. Another differential equation. Fourth derivative of x with respect to t, right? Okay. I write this from your textbook, right? 5 times d square x over dt square plus 3x equals sine t, right? Okay. Another one. This is partial derivation. dv over ds plus dv over dt equals v. And final one, second partial derivative of u with respect to x. Again, second partial derivative of u with respect to y, and third term with respect to second derivative with respect to partial derivative with respect to z, we set is equal to 0. So these are examples, right? Examples of differential equations, right? Okay. So another definition of differential equations, we can say that a differential equation involving ordinary derivatives of one or more dependent variables with respect to a single independent variable is called an ordinary differential equation. Okay. So in that case, okay, equations 1, so let me label this 1, 2, 3, and 4. Okay, so we classify differential equations, so ordinary or partial. So this is a classification according to derivation, ordinary or partial. Okay, look at that. Again, let me remind the definition. Let me state the definition, I'm sorry. A differential equation involving ordinary derivatives of one or more dependent variables with respect to a single independent variable is called ordinary differential equation. And first of all, let me tell you that in this equation, y is independent. Well, I am sorry, y is dependent. I am sorry. Dependent variable. X is independent. So this is a differential equation involving ordinary derivatives of one or more dependent variables. So this satisfies this definition. So what we can say that this and this, also this is the x is in this time in this equation, x is dependent, right? Dependent, and t is independent. Independent variable, right? Okay, so this is here. These two are ordinary differential equations, right? Ordinary. These are ordinary differential equations. Okay. So now another definition. Definition of partial differential equation. A differential equation involving partial derivatives of one or more dependent variables with respect to more than one independent variable is called a partial differential equation. So these two partial differential equations, right? Partial. Partial, right? Okay. So in this equation, v dependent, right? And s and t independent. So here u depends on three independent variable x, y, z, right? Okay, so this here partial differential equation. Okay, having said that, let me talk about another classification. The order of highest order derivative involving a differential equation is called order of differential equation. Okay, so let's talk about the order of differential equation. So the order of this differential equation, let's look at the definition. The order of highest order derivative, which is 2, right, second, involved in a differential equation is called order of the differential equation. So this is second order differential equation, right? Second order. This one, how about this one? So derivative of the highest order derivative defines the order, which is 4, right? This is fourth order. Fourth order ordinary differential equation. This is second order ordinary differential equation. How about here? This is here first order, right? That is first derivative. First order partial differential equation, we say. Okay. So how about this one? This is second order, right? Second order. So this is another classification according to order of a differential equation. First order, second order, third, fourth, whatever. And another classification, ordinary and partial. Okay. Now let's continue. Now we are going to study an important concept here. Important concept. Linearity and non-linearity. Okay. A linear ordinary differential equation of order n in the dependent variable y and independent variable x is an equation that is in or can be expressed in the form, in this form. So any differential equation which can be expressed in this form. So let me state that we study linearity. So we study linearity and non-linearity. So any differential equation which can be put in this form is called linear ordinary differential equation of order n. So this is a0, which is a coefficient, and derivative with respect to x, a1 another coefficient, right? dn minus 1 y or dxn minus 1, and so on, n minus 1 x dy over dx plus an xy equals bx. Okay, so we observe that the dependent variable y and its various derivatives occur to the first degree only. So the dependent variable y and its various derivatives occur to the first degree only. Okay. And 3, the no transcendental functions of y and or its derivatives occur. Okay. Let me give you an example. So these are ordinary differential equations which are both linear. So I'm going to write down linear differential equations. Example. Another one. These are all linear differential equations. Okay. A nonlinear, so these are linear differential equations. A nonlinear ordinary nonlinear ordinary differential equation is an ordinary differential equation that is not linear. So if it is not linear, then it is linear, right? Oh, non-linear, I'm sorry. It is not linear, then it is non-linear. Okay. So let's continue. So let me give you some examples of non-linear differential equations. Okay. So these are the these are the examples. So, all these are nonlinear differential equations. So look at that equation. So let me label this one. Okay, not one, because we already used one in the previous page. 5, 6, and 7. Okay. So this first one, this is 50. Number 5 is nonlinear because the dependent variable y appears to the second degree in term 6y squared. So this is nonlinear because the dependent variable y appears to the second degree in the term 6y squared. Okay. So this makes it nonlinear. Okay. So this second one owes its nonlinearity to the presence of the term 5, and this term makes it nonlinear, right? Finally, this is nonlinear because of the term, this term, product of y dy, the product of y with its derivative, which involves the product of the dependent variable and its first derivative. So because of these terms, these equations are nonlinear. Okay. Okay. Now origin and application of differential equations. Okay. So let me cite this. Let me cite this from textbook. So okay. So differential equations occur in connection with numerous problems that are encountered in various branches of science and engineering. So first one, we can apply differential equations to the problem of determining the motion of a projectile in rocket, satellite, or planet. Okay. So let me underline this. The problem of determining the charge or current in an electric circuit, right? So again, we can easily do this by using differential equations. The problem of conduction of heat in rod and in a slab. Problem of conduction. The problem of determining the variations of a wire or a membrane. These are applications, right? We read from textbook. Okay, the study of the rate of the composition of a radioactive substance or the rate of growth of population. The study of the reactions of chemicals. The problem of determining of curves that are certain geometrical properties. Okay. So these are some of the applications possibly with differential equations, right? Okay. Okay, now we study origin and application of differential equations. So differential equations occur in connection with many problems. Some of them, let me list some of them. The problem of finding the motion of a projectile. Okay, this is projectile motion, right? We study in physics 2. Physics 1, right? And second problem, in physics 2 we study the problem of finding the charge or current in an electric circuit, right? So remember RC circuits especially. We have a differential equation there, okay? So for the projectile motion, we have Newton's second law, right? MA, but in one dimension, the acceleration is the second derivative of position with respect to time. So this is a differential equation, right? Newton's second law, well-known Newton's second law with projectile motion. And the second one, RC circuits, right? In RC circuits, as we know, current is the derivative of charge, right? So this is a simple differential equation. So we can extend this list, right? So this list can be extended. So for example, let's look at the list in your textbook. So third example, the problem of conduction of heat in a rod or in a slab. So conduction of heat. Conduction of heat and vibrations, right? The problem of determining the vibrations of a wire, right? So vibrations of wire. Vibrations of wire. So now we are done with this first section of the chapter 1. First section of chapter 1. Now we continue to conclude this chapter. We should look at some examples on this chapter. And we are going to decide, we are given some differential equations, and we are going to decide whether these equations ordinary or partial, nonlinear or linear. Okay. So I am going to look at some of them. So dy dx plus x squared y x e to the power of x. So this is of course ordinary differential equation, right? One independent variable, right? Ordinary and nonlinear. Why? Because we have a term like this, right? X squared y. So this is nonlinear, right? Okay. How about the second one? This is the equation. D square u over dx square, d square u over dy square. So this is linear and partial. Okay.
Okay, now we study solutions to differential equations. Solutions to differential equations. So we distinguish two types of solutions: explicit and implicit. Implicit. So let's look at the definitions of these explicit and implicit solutions in your textbook. What are the definitions? Okay, so let me read from your textbook definition. So let's consider nth order ordinary differential equation. So f is real here. This differential equation is real. Function of its n plus 2 arguments. So now let me give you the explicit definition of explicit solution. So the function f is called an explicit solution of the differential equation of this differential equation on I if it fulfills the following two requirements. First of all, f is defined for all x belongs to I, and we set f equals to 0 for all x belongs to I. So in that case, this function f lowercase is an explicit solution. On the other hand, a relation gxy equals to 0 is called an implicit solution of this differential equation 110 if this relation defines at least one real function f of the variable x on an interval I such that this function is an explicit solution.
So this is an example. So we want to show that f, the function f, given by this expression, is a solution of the differential equation. Okay. So let's take the derivative of this first. And second derivative. Let me place this into that differential equation. It's cancel, and this reduces to identity. Okay, which holds for all real x. So that's why the function f, okay, defined by this expression, is an explicit solution of the differential equation for all real x. Okay, explicit solution. Now let's look at another example. So we are given this relation here. Okay. So we want to show that this relation is an explicit, this expression is an implicit solution of the differential equation. Show that this solution So we want to show that this is an implicit solution of this differential equation. Okay, on the interval from -5 to 5, right? Okay. So what we can do, we can write this down as f1x equals or f2 okay. So if we take the first derivative of f1, let's first show that f1 is an explicit solution of this differential equation, right? So let's take the derivative. So if we place this solution into that equation, so we get an identity, right? So this means that f1 is an explicit solution of this differential equation. On the other hand, this solution is an implicit solution. Okay. Also, we can show the same for f2. So f2 also an explicit solution. Okay. Explicit solution of this differential equation. This is implicit, right? But these are explicit. So let's look at an example. So this is our differential equation. E to the power of x y dx plus e to the power of minus 3x square root of y dy equals to 0. So we are looking for a general solution to this differential equation, right? So what we do, we divide both sides by e to the power of minus 3x. So what we get here, e to the power of 4x times y, right? We divide also with y. Okay, so dx plus this cancel, square root of y over y dy. So this gives me dy over square root of y. And now we integrate both sides. This gives me plus y plus 1 equals to, and also we set this equal to an integration constant, right? Integration constant. See. So let's multiply both sides by 4. Another constant, and 4 times c, let's call this another constant k. So this is the general solution, right? General solution to the differential equation.